Okay, which ones are we gonna go over? Huh? 20,
26 and 30.
26 and
30.
30, okay. And then with the answers, you couldn't figure out.
Yeah.
26. Seems like this week everybody's tired.
I'm sick, remember?
No, but just like everybody in general. Write an equation for the surface obtained by I think this problem's on the test. Here is a parabola, and you're gonna revolve it about the z-axis. So wait, did I write this correctly? Oh yeah. So here, so this is like 4z is equal to y squared, yeah? So in the yz plane, okay, let's just say y and z look like this. In the yz plane, this would be a parabola opening which way?
26.
This is 20, I wrote down the wrong one?
No, you're
Oh,
right.
never mind, I tried to solve 27.
Oh.
Okay, which way does this parabola open in the yz plane?
Upward.
Up, down, left, or right?
Oh, never mind.
No.
Right.
1 out of 4 chance.
Right.
To the right, it's like this. First of all, you guys gotta see that.
Wait. Okay, I see.
Okay, now, in 3 dimensions, see how like I start with 2 dimensions and then so where is the YZ plane? Oh, that would be, so it's like right here. Here's the parabola. And then it says we're gonna revolve it about the Z-axis.
Do you usually draw it below the
No.
y-axis, or it's just because we're resolving it?
No, I don't, no. I just, because it's opening to the right like that, yeah. Okay, so if you revolve this about the z-axis, you're just gonna get this, what do you even call this thing?
Oh, I forgot.
That's not a graph we learned, yeah? Anyway, how do we revolve something about the z-axis? What do we have to find, the equation? About the z-axis. How do you what do we revolve it about the z-axis?
Now, what if you looked at the traces? Does that work?
The traces. I don't know. I'm trying to think of the traces. No, there must be something you can
Wait,
just do to the equation.
Wait, no, because that would be the trace for the yz plane, and then if you, the xz plane would be the same one, but with x instead of y, right?
Okay, I agree with that. You understand what he's saying? So like if you revolved it around, then the xz trace is gonna be the same, it's like the same, like, right? It's still a parabola, right? So in the xz plane, wouldn't the equation then be x equal 4z squared then? No,
Wait,
4x equals z squared. Is that right?
what is it?
In the xz plane.
What is it? 4z minus x squared.
Wait, I'm thinking 4x equals z squared. Or is it 4z equal x squared?
Yeah, I think it's 4z equals x squared because it's the same thing.
Oh, yeah, you're right. 4z equal x squared. So that's the trace in the xz plane.
The xy plane would just be a point, right?
Mm-hmm. No, I'm just thinking, isn't there like just something you can do to the equation to get the answer if you revolve it about something, or you just have to think about it?
Wasn't this from calculus?
No, that's finding the volume of it. See, that would be much easier, finding the volume, but writing the equation.
Oh,
Okay, tell me the answer. What was the answer?
The answer is just add the tree.
Hmm?
Wouldn't it be like 4z minus x squared minus y squared.
Okay, say that again?
I don't know what the answer is.
Oh.
But that's.
What do I give you guys the answers?
What's the 26?
26.
X squared plus y squared minus 4z equals 0.
Ah, knew it. Cause then you just add the traces, but you would only.
But wait, that's a paraboloid though.
It's the same thing. If you 4z minus y squared minus x squared, it's the same thing.
That's not this, because look, this parabola is concave that way, right?
It's just paraboloid of one revolution.
See, if it is a do we have our concavity wrong then? Is our concavity wrong on this graph? Right here? In the y, no, this one here. In the YZ plane, is the parabola going that way or that way?
I think that's correct.
That's correct. So then when you revolve it around the z-axis, you're gonna get this. And that's not a parabola. A paraboloid will go like this, will go that way. Right? So that's not the right answer because that's a parabola.
Wait, no, but doesn't it make sense that would be the answer? Because if the xy trace is no x, or no, the xz trace is no x, and then the yz trace is, no, if the yz trace is no x, and the,
Oh yeah, but according to this, the YZ trace would be that though, yeah?
No,
Yeah.
it's just that our graph is wrong.
That graph is wrong then.
How do you?
It has to be.
Our answer's right, the graph is wrong.
yeah.
What do you mean the graph is wrong? That graph.
Yeah.
Oh yeah, it is that way.
Oh.
It's off.
Also,
Wait, let me think.
It's off.
Okay, if you were to open upward, it
Because
would be
what's
z equal, yeah! We had it wrong from the beginning. Okay, then that's right. Oh, that was a lot of wasted
So
time.
we said upwards is
So-
right.
The parabola is, oh, what am I talking about? YZ. That's dumb. So it is just a paraboloid like that then.
How do you write an equation?
because if you, isn't it because like if you have no x value in the yz trace, and then you have no y value in the xz trace, and you're just like add.
Yeah, so you want an equation whose xz trace, I mean yz trace is that, but whose xz trace is that. Right? And it's gonna be a paraboloid. Or how about just know it's gonna be a paraboloid and then look at the equation, right? Right? Since it's, oh, this is dumb. Since it's gonna be that way. Okay, is there a way we can just put it together somehow instead of just having to think about it? I would think there's a mechanical way of doing it. No, I guess not. I guess you gotta just think, yeah? Okay, write an equation whose
Wait,
YZ trace is that,
Wait, no, that makes
but
sense.
the XZ trace is that, so then it has to be that.
Wait, doesn't it make sense though? Because then you just have a circle. If you did x squared equals 4z minus y squared.
Okay,
then
say that again, x squared?
equals 4z minus y squared. It would just be a circle in the x.
This is just that equation though, right?
Yeah, but then wouldn't that just mean that like the radius of the circle would be the square root of 4z
Yeah,
minus 4
yeah.
squared, and then it would just like,
So the higher up you go, the bigger the radius gets, right?
yeah.
Yeah, but then how do we get that equation though, that's the
They
thing.
just said it equal to x squared.
What do you mean?
I don't know, I was going somewhere, but I forgot where.
Okay, we gotta think about this then. Okay, what's the next number? 30. The parabolic cylinder y squared plus z minus 4 equals 0 intersects the elliptic paraboloid x squared plus 3y squared minus z equals 0 in a curve determine the projection of C onto the xy plane. Now, this is an important skill for later, because later we're gonna be doing triple integrals, and by projecting the thing down to the xy plane, that's how you're gonna get your limits of integration. Did you make it that far? Joe?
Isn't that volume?
Yeah, so we're gonna do triple integrals to compute volumes and centroids and things like that, but, so wherever the graphs intersect, you have to like smash it down onto the xy plane. That's what this problem is doing. So, you guys understand what I'm talking about? Like over here, if you cut, like, where does this paraboloid intersect like the plane z equals something? It's gonna intersect it in a circle, right? If you were to take that circle and smash it down onto the xy plane over there, what's the equation of that circle? That's what you gotta find out. So that's what we're doing in this problem. Like I'm not sure where, I mean, it's very difficult to graph this, but wherever they intersect, what happens when you smash it down onto the xy plane? That's gonna be key. So first of all, how do you figure out where these graphs intersect? What would you do? Wouldn't you equate the z's? You can solve for z in this equation. Z is equal to 4 minus y squared. Solve for z in this equation and you get x squared plus 3y squared. And then equate the z's. 4 minus y squared is equal to x squared plus 3y squared. And then you got 4 equals x squared plus 4y squared. And if you want to, you can go x squared, divide everything by 4. There you go. See how it only has x's and y's? So that means it's in the xy plane. That would be the thing in the xy plane. This is an ellipse. Is that the answer?
Wait, how do you graph it?
The ellipse?
The intersection?
Oh, shoot, I wouldn't even begin to attempt that. Okay, you want to try it just for funsies?
Wait, is that just the answer?
Oh, yeah, that's it.
Yeah.
I thought it
Because
was
look,
like
it just got x's and y's in it, right?
That was, this is the projection.
So they intersect somewhere, like, I don't know, it could be at an angle or some weird angle, but then, so it's gonna be an ellipse like this. If you smash, so they intersect over here, you smash it down onto the xy plane, that's gonna give you your limits of integration later on. So this is, like I said, an important skill. Anyway, you know what, we're not gonna even attempt to graph that, no. That's just crazy, that's crazy. Too difficult. But there's probably some multivariable calculus professor somewhere, maybe MIT or something, they probably could graph it because they spent their entire life doing it. I'm not going to attempt to do it. Okay, what are we learning today then? Today is easy.
16.4.
16.4, partial derivatives. Okay, let's scroll to that place. Partial derivatives. So now we have a function of several variables.
Yeah, when are tests correct?
Today.
By the end of class today,
In a class?
I think I sent you guys an email, didn't I?
No, it's like,
Wait, I don't have any free periods yesterday. Oh wait, I did.
Well, I was gonna give you time in class
I
today.
only have one more problem, it's fine.
Huh?
I only have one more problem to do.
Yeah, everybody did pretty well, right?
Can I do it in period 3?
Is that the end of period 7?
No.
You guys are killing me. Okay, let's just do the example in the book then, right here. You have a function of x and y. You can think of that as z if you want to. 3x squared y minus 5. I can teach this to you how to do it in like 5 minutes or even less. Okay, so if you want to, you can think of that as z and you can graph this. It's going to be some kind of surface. Yeah? So what we want to do is we want to compute partial derivatives. What's the partial derivative of f with respect to x? That's the way we write it, f sub x, like that. What is the partial derivative of f with respect to x? Now you can probably guess what that is. You're going to treat x as the variable. Any other variable will be constant. In this case, so you treat y like a constant. So when you take the derivative of that, do I need to use the product rule? No, because now y is constant. So you can throw the 3y on the side like an unwanted pet, and then you take the derivative of x. See, because you're taking the derivative with respect to x.
Can you draw a visual representation?
Yeah, well, I have a hard time drawing that kind of stuff. Anyway, the book has a pretty good picture that we'll look at, okay? Minus, now, x is your variable, y is a constant, so 5 cosine pi y, that's a constant. You throw it on the side like an unwanted pet, and then you multiply it by the derivative of x, which of course is 1. There you go, that's the partial of f with respect to x. And then, of course, we can do this. What is the partial of f with respect to y? That means you now treat x as a constant. So, if x is a constant, then see, 3x squared is a constant. Throw it on the side like an unwanted pet. The derivative of y is simply 1. You guys get it? It's pretty simple. You just treat everything else as constants. And then, this is your variable now. Negative 5x is a constant. What's the derivative of cosine pi y with respect to y? What's negative sine pi y times the derivative of pi y, which is pi. Boom. So that would be the partial derivative of f with respect to y. And then, on tonight's homework, you're going to be given a function of 3 variables. Yeah, I'll just make up my own. Scroll. What if you have a function of 3 variables? That means if you were to graph this, this would be a 4-dimensional figure. Right? Okay, so, oh gosh, what shall we do? X squared, y squared, no, cube z to the 4th plus secant xy. Okay, let's just do that. Oh, let's put in a z thing. Plus, what can we do? Minus z squared. Whatever. We can graph that on Wolfram alpha if we have to. Okay, so what's the partial of this function with respect to x? So x is your variable. All other variables are constant. Okay, so everybody's going to do one. F sub x.
Y cubed z 4 2x.
Okay. Keep going.
Oh. Secant xy. Oh, times, or no. 10 xy times y.
Times y. And then,
Minus, oh wait, no, zero.
yeah, minus 0. There you go, that's correct. What is the partial of f with respect to y? Y.
X squared, 0 4, 3y squared, plus x secant x y 10 xy.
Mm-hmm. Minus 0. Yeah, because z is a constant, yeah? And then what's the partial of f with respect to z? Cho.
X squared, y cubed, 4z cubed,
Okay.
and then 0
Okay.
plus 2z.
No, minus 2z.
Oh, minus 2.
Yeah, there you go. It's so, mechanically it's easy to do, but what does this mean? Like, okay, we're not gonna think of this one as 4-dimensional graphs. Right? It's just hard to imagine. So this is a surface, so when you take the derivative of f with respect to x, you're computing the slope of the graph when y is constant. But see, there's lots of times when y is constant. So here, you know what? I'm going to attempt to draw it. So let's say you have some kind of surface. Gosh, I can't even. How do we draw a 3-dimensional? Okay, here. The surface is like this. Now, if you kept y constant, y could be 0, y could be 1, y could be 2, y could be 3, right? As long as y is constant. So let's just say y is 1. So let's say you have the surface, but what happens when the y coordinate is 1? When you intersect it with the plane y equal 1? Aren't you going to get, like, whatever the cross section is? So the derivative of f with respect to x gives you the slope of the graph when y is 1, right there, or when y is 2. Well, if you keep y constant. So every time, whatever the surface looks like, if you intersect it with the plane, y equals 0, y equal 1, y equal 2, y equal 3, whatever, and so forth, It gives you the slope of the graph in that plane. Anyway, the book has a graph. I don't know if it got copied right. And you guys watching on video, turn to page, there it is right there, 677. Tried to get both pictures in the screen, but I can't make it smaller. We'll look at it one more time. Which one is better? Okay, there. So that's exactly what I'm talking about. Look, you have your surface over here, and then y is constant. So it looks like in their picture y could be like 2 or 3 or something like that. So when you intersect the plane, see how you have this curve like this right there? That partial derivative gives you the slope along this curve in that plane when y is constant. Right?
But it gives you the slope of that curve, or it gives you that curve?
No, it gives you the slope of that curve. Keeping y constant though. See, because when you have a three-dimensional surface, see like right here, when you intersect it with the plane, you get this, see that's a two-dimensional graph, right? The partial derivative gives you the slope of that curve right there. But see, the thing is, like with a three-dimensional surface, what is slope? We don't know what slope, in three-dimensional surfaces, what is slope? Well, if you keep y constant, you can figure out a slope, or if you keep x constant, you can compute a slope. But the entire three-dimensional surface, there is no slope. So what is slope in 3 dimensions?
Isn't it like a vector?
Yeah, it's a vector, but that's the next chapter. It's called the gradient. In fact, I'll just tell you now, like, if you have a surface, like you have a local maximum point over here, how are you going to locate this local maximum point? When the tangent plane is parallel to the xy plane, right? Right? So you have the xy plane on the floor. So where is the tangent plane going to be parallel to the xy plane? That's where you find maximums and minimums. That's what we're going to do next chapter. So basically, if the tangent plane is parallel to the xy plane, that means the perpendicular vector is going to point straight up then, right? That means the x and the y component of the perpendicular vector, we call this the gradient, has to be pointing straight up. But you don't have to worry about that now. And how do we find this perpendicular vector or parallel plane? I mean parallel to the xy plane? By doing partial derivatives. So tonight's homework, you're just going to be doing partial derivatives, only first derivatives. And then, do I see you guys on Tuesday? Yeah, I do. Then on Tuesday, we're going to compute, like, is there like a second derivative for this? Yeah, it's called the mixed partial. Or the second partials. We're going to learn how to do that next week. It's really easy. You just take another derivative. But then you're going to ask yourself, well, if I took a derivative of this with respect to x again, what if I took it with respect to y? In other words, what happens if you take the derivative with respect to x first, but then the second one you take it with respect to y? And what if you took the derivative with respect to x first and you did it again with respect to x? So you got these different kinds of second derivatives. And it's easy to compute, but then to visualize is just another story. Okay, so tonight's homework, all you gotta do is compute partial derivatives. It's really simple. Look at the problems. I don't think there's anything exotic in there. Where's the problems? Oh, I forgot to tell you. This other notation. This symbol, this is, I guess, like Leibniz's notation. So like, if this is f, we can also write it like this: the partial of f with respect to x. See, it kind of looks like a d, like regular derivatives, dy dx. But then when you're doing partials, we write this symbol. That looks like a Greek. You guys know any Greek letters? I know some, but that one doesn't look familiar. Anyway, that's the symbol. I don't know, maybe that's just a made-up symbol, but that's the symbol for the partial of f with respect to x, or you can also write it like this.
And that's like an f subscript x.
Yeah, sounds good. All right, so like, yeah, I don't think there's anything there. It's kind of easy. Hey, it looks like some of these problems are on the test. That's what it looks like. All right, we're done.